Quantum physics. It sounds intimidating, right? It's the science of things so small they're almost impossible to imagine. And yet, it's probably the most powerful and revolutionary idea of the last century. It's a science that hasn't just moved our understanding of the universe, it has literally changed how we move through our world. So let's dive in.
So, back in 2015, humanity felt something absolutely extraordinary. We detected the collision of two massive black holes. An event so powerful it released more energy in a single moment than every star in the known universe combined. But how did we feel this cosmic smash-up? We felt it through something called gravitational waves.
Now, these aren't like waves in the ocean. They aren't moving through space. They are literally waves of space itself. Just try to picture that for a second. The very fabric of reality stretching and squeezing as this ripple passes through. The problem is, by the time these things get to us from billions of light years away, they are incredibly, almost impossibly faint.
And that right there is the big question. How in the world do you measure something like that? To get the answer, we have to leave the massive scale of colliding black holes and travel all the way down into the strange, totally counterintuitive world of the very, very small. The answer is all wrapped up in the weirdness of quantum physics.
Okay, so the first thing you have to get your head around is that the quantum world, well, it just doesn't play by our rules. You have to make a complete shift in your thinking, away from the nice, predictable world we see every single day.
For centuries, we basically saw the universe as this giant, predictable clockwork machine. You know, if you knew exactly how you threw a ball, you could predict exactly where it would land. Everything was cause and effect. But quantum physics just threw that whole idea right out the window. Down at the level of atoms and electrons, reality is more like a game of chance. You can only know the odds of something happening, not what will happen.
And this idea was really, really unsettling, even to the absolute greatest minds of the time. I mean, Einstein himself hated it. This famous quote from him just perfectly captures that feeling of, no way, the universe can't be random at its core. But, oh, the weirdness doesn't stop there.
This is where that dice roll actually happens. Before you measure a particle, like an electron, it isn't really in any one specific place. It kind of exists as this cloud of possibilities. It's here and there and everywhere, all at the same time. The very act of looking at it is what forces it to, pick a spot.
And then there's entanglement. Just imagine you have two coins that are magically connected. If you flip one and it lands on heads, you instantly know, faster than light, that its partner is also heads, even if that other coin is on the far side of the galaxy. That instant connection is what Einstein called spooky action at a distance, and it completely breaks our everyday sense of how things should work.
So, okay, we've got probabilities, we've got superposition, we've got spooky connections. It all sounds a bit like science fiction, doesn't it? But here's the crucial part. Scientists didn't just scratch their heads at all this strangeness, they actually learned how to control it. They learned how to build technologies that have totally reshaped our world.
Take the laser, for instance. A laser is a purely quantum machine. Its magic comes from something called stimulated emission. It basically starts when one little particle of light, a photon, zips past an excited atom and nudges it into releasing a perfect clone of that photon. Then those two photons find two more atoms, and suddenly you have a cascade, creating this perfectly ordered, incredibly powerful beam of pure light. And that quantum process, that perfect cloning, is what gives lasers their unbelievable precision. And guess what? That precision is exactly what we needed to build the LIGO observatories, these giant instruments that can measure a distortion in space-time thousands of times smaller than a single proton. We actually harness the quantum world to see the cosmic one.
Now let's talk about another world-moving technology, the atomic clock. If you want to measure movement, you have to be able to measure time with incredible accuracy. So instead of a swinging pendulum, an atomic clock uses the perfectly consistent tick of an atom's natural quantum state. This is so reliable, it literally gives us the standard for time itself.
So why does that matter to you and me? Well, that quantum heartbeat is what runs the entire GPS network. There are satellites whizzing overhead with these atomic clocks on board, sending out timed signals. Your phone picks them up, calculates the tiny differences in their arrival times, and pinpoints your location. So yeah, every single time you use a map to move from point A to point B, you are using quantum physics.
And the level of precision we're talking about now is just staggering. Modern optical clocks are so ridiculously accurate they can measure one of Einstein's weirdest predictions, that time actually moves at different speeds depending on gravity.
I mean, if you move one of these clocks up by just the width of a human hair, it will detect time speeding up. Just a tiny, tiny bit. That's mind-blowing. So quantum mechanics has already given us lasers and GPS, completely changing how we see the universe and how we move through our own world. But what's the next big thing? What's the next quantum leap? Well, for a lot of people, the answer is quantum computing. Your computer, your phone, everything you're used to works with bits. They're just simple on or off switches, a 0 or a 1. But a quantum computer uses a qubit. And thanks to that wacky idea of superposition, a qubit can be a 0, a 1, or, get this, a blend of both at the exact same time. This just cracks open a whole new universe of what's possible with computation.
And the power just grows exponentially. When you start linking these qubits together with entanglement, their complexity just skyrockets at this mind-boggling rate. As the physicist John Preskill said, if you wanted to describe just a few hundred entangled qubits, you would need to write down more classical bits than there are atoms in the entire visible universe. Just think about that. That's the insane amount of computational space these machines can work with.
So you won't be checking your email on a quantum computer, at least not anytime soon. These are highly specialized tools for really specific jobs. Because they run on quantum rules, they're perfect for solving quantum-level problems, like figuring out exactly how a new drug will work in the body, or designing revolutionary new materials, one atom at a time. They can take on a level of complexity that would basically melt even the world's most powerful supercomputers.
So, from totally redefining reality itself to giving us the tools to map the cosmos and navigate our own planet, the science of the very small has moved our world in truly profound ways. It took us from this cozy, predictable, clockwork universe to the strange, probabilistic, digital world we live in today. And so the question we're left with is, as we get better and better at harnessing all this quantum strangeness, where is it going to move us next?